another one. Sorry.
Okay.
Thank you. So I think there is a general consensus, at least in this conference, that information geometry is about affine manifolds. We had a lot of talks talking about this subject, some of them at a considerable level of sophistication. Now, from the point of view of mathematical statistics, this affine structure is, I believe, quite natural, and even more natural that the structure derived from the Rao argument about the Riemannian structure. So what I'm going to make very briefly is to try to show to my statistician colleague that an affine structure is exactly what she needs to do the usual job as a statistician. So when I think of affine space, I think that the original definition of affine space is Weil, 1921. And the fact that information geometry is about an affine structure is proved, first of all, by the presentation of Amari in the 80s. And also there is a presentation of affine differential geometry based on the definition by Weil in Nomizu Sasaki. And Nomizu Sasaki recognized that Amari is a special instance of their theory, actually. So I want to show that the affine structure is natural from the point of view of mathematical statistics, and indeed gives a very natural treatment of a classical problem like the notion of effect and interaction as treated, for example, in contingency tables, for example, by Feinberg in 1980, and also in the problem of a model with fixed marginals, as the famous Kantorovich problem. And the idea that it is interesting to have an affine space in order to do something like a gradient descent to solve optimization problem of interest is, for example, in the so-called regularization method to solve to find versatile distance by Perret and Couturi. So what is an affine space? According to the original definition and according to what my teacher in physics told me in the secondary school, an affine space is a set M and the real finite dimensional vector space, and you have a mapping from couples PQ of points to a vector, which is called the vector from P to Q, which is, the points are not in a vector space, but the vector is. And the condition are that if you fix the original point, the mapping is 1-to-1, and in the classical case also onto. and the parallelogram law holds. And so the affine space is exactly this structure. The set is a vector space, and this translation or difference operator. And actually the translation operator with a fixed initial point gives an atlas of charts. And this atlas chart is an affine atlas because all change of coordinates is actually a translation. So now to do something more sophisticated, we need a slightly more general definition covering the case where we are in a curved space, and the vector space is not, it's changed for each initial point, and each initial point there is a tangent space, for example, on a space. So one has to slightly update the original definition, moving from a trivial bundle M times V to a non-trivial bundle. So a affine space in this sense is a set M and a family of topological vector spaces, one for each point of the set. And moreover, we need from the beginning a family of topological linear isomorphism, the translations from one space to the other. So now the difference is again a mapping from nu to an element of the vector space centered at nu, such that the mapping for a fixed initial point is injective. And we have to modify the parallelogram law because the vector from mu1 to mu2 and the vector from mu2 and mu3 are not in the same vector space, so you have to move it in a parallel way somewhere else. So now this gives an affine manifold. You compute the change of coordinates, and you find that the translation are exactly the linear part of an affine transformation of spaces. And to get an affine manifold, now I am also trying to do a construction such that the construction is non-parametric. So I have to be very careful about which kind of topology I can implement on my spaces. Otherwise, the model would apply only to the final state space case. So we have to assume that the mapping the mapping S from one point to another point is such that the image is a neighborhood of zero. And so we can have an open, restrict to an open set and construct a general manifold from these atlases. A manifold, a non-parametric manifold in the sense of Lang. In the sense of Lang, a manifold is not defined by modeling all the charts of the same vector space, but there can be different vector space, but the vector space have to be top linear isomorphic. So given that we need only a little step more to observe that we can take together the point mu and the vector v to define an affine bundle. And the other affine bundle has naturally his own chart, system of chart. And this is actually what Goffredo was presenting a moment ago. So now the advantage of this construction is that you can define immediately all the kinematics for the velocity of a smooth curve is defined through the vector operation by representing taking a curve at point gamma t plus h, computing the vector with respect to some other points gamma of t, and then taking the derivative. And this is the velocity in the affine space. Now, you need, at this moment, you add another ingredient, and the other ingredient is not spelled out here. The second ingredient is that now you have your vector spaces, and you take a duality pairing of these vector spaces with other vector spaces in a duality pairing. And this allows you to define in the standard way the gradient of a function. So why this is interesting? This is interesting because first now I am able to say what it is a gradient flow. And secondly, I can make the observation that the affine bundle is itself an affine space. And then I can go on one step and get the second order calculus in some sense for free from this construction. Now, what the interest of this construction coming from physics for the statisticians? The interest is the following, that following arguments basically due to Roland Fisher in the 30s, you can construct an affine space whose ingredients are directly inspired from, say, the statistical wisdom. So you take, for example, the set of positive probability function on a finite sample space, and then you construct your difference on mapping the following way. First of all, you compute Q upon P. This is, in statistics, is the likelihood. And the idea from statistics is that you cannot use frequencies directly, because in some sense you have to compare your frequencies with some ground state, a reference state. So first you compute the likelihood. The likelihood is Q upon P. And the second rule is that you never look at the frequencies directly, because Euclidean geometry does not have any sense for frequency. So first you take the logarithm. That's the statistician recipe. At this point, you have a random variable, which is logarithm Q upon P. And you, as a statistician, first you compute the mean value. And the mean value, expected value at P of log Q upon P, which actually happens to be a very natural object, precisely minus the curve divergence. And second, you compute the variation. That is, in statistics, you have a random variable, you compute the mean and then take the difference. And the difference represents the variation. So the vector is the variation. Now we have to check if this works, and actually it works, because if you take for each distribution P the set of centered random variable, this is what in statistics is called an effect, because of the use in experimental design. And each probability has its own effect space. And you move from one effect space to the other by recentering the random variable. So the idea is that to use the transport as a centering. And it's quite interesting that with this choice, if you compute the dual of the transformation of this transport, you find another very interesting object. It's the change of density. Now, with these rules, strangely enough, the parallelogram law holds true. So this is an affine space, and that in some sense, this is a big discovery of Roland Fisher, actually, that was the first to devise this mechanism in statistics. And then you can compute the inverse charts, and the inverse charts, again, are a very natural object, are just the exponential families. That's so the one chart goes from for an effect to a random variable, and the inverse charts goes from the effect to a distribution. There is a normalizing constant, which is again exactly what we need. Is a convex functional that you can use to show that actually your affine manifold is an Hessian manifold. And if you derive 3 times this functional, you get the third moment. And I learned yesterday, or I learned this morning, that this means that this manifold is an F manifold, actually. And finally, if you compute the velocity, according to this scheme, you get what Fisher calls a score. That is the derivative of the logarithm of the curve. This is a score, that score. And at this moment, if you want to, the score is a sort of according to Fisher, is the evaluation of the variation of the distribution in according to the parameter t. And if you want to compute how big is this variation, you compute the variance, and the variance is the Fisher information. So the Fisher information comes at the end of these constructions, not at the beginning. So at the beginning, in my opinion, there is this strange combination of choices. Maybe I have lost my time.
Okay.
I am already out, or?
Yes, you are. Can you please wrap up, because we will miss the coffee break.
Okay. So I just say a couple of words. You can apply this to the special case where the space, the space is a factor space. There are 2 factors, and in this case, you can specify special models, for example, fixed marginals. This gives rise to a submanifold, and you can compute the geometry of this submanifold. And the geometry of this submanifold consists in the description of the tangent space in the sense of the affine manifold. And the vectors in the tangent space, in this case, are what in statistics is called an interaction. That is a random variable such that the conditional expectation with respect to the 2 margins are 0 in a given distribution. Thank you. Sorry about being so long.
No problem.